The power grid fails at 2:17 a.m. Elevators freeze between floors. Emergency lights flicker on in long, carpeted corridors. Electronic door locks default to safe mode. Outside, traffic signals die, cell towers switch to battery. And within hours, the fragile choreography of supply chains begins to unravel. In cities, millions of people wake up to a silent infrastructure that was never designed to run without constant energy input. Refrigeration stops. Water pressure begins to drop. Fuel pumps are useless without electricity. The question becomes brutally simple. Where can human beings concentrate shelter, security, water access, and structural protection without having planned for it? The answer is not romantic. It is not rural cabins or improvised bunkers. It is the most ordinary urban building type people overlook every day, the modern hotel. Hotels were never designed as doomsday refuges. They were built for short-term occupancy, liability management, and brand consistency. Yet when you analyze them through the lens of structural engineering, life safety codes, logistics design, and emergency management science, an unsettling realization emerges. The features that make them efficient hospitality machines also make them uniquely resilient shelters during systemic collapse. This is not speculation. It is embedded in building codes, plumbing standards, fire protection engineering, and decades of disaster response data. The first overlooked factor is structural redundancy. Most mid to high-rise hotels are constructed to commercial occupancy standards, not residential minimums. In the United States, for example, they fall under international building code classifications that require stricter fire resistance ratings, compartmentalization, and load calculations than typical apartment complexes. Reinforced concrete shear walls, steel framing, and engineered floor assemblies are common in multi-story properties. These buildings are designed to withstand heavy occupancy loads, moving luggage, banquet gatherings, and conference assemblies. That translates into load-bearing margins that exceed those of many residential structures. In seismic regions, hotels are often retrofitted or designed with lateral bracing systems because they house transient populations and face higher liability exposure. The misunderstanding is that a hotel is simply a stack of rooms. In reality, it is a commercial-grade life safety structure built to survive fire, wind, and crowd stress. The hidden science lies in redundancy factors and safety coefficients. Engineers overbuild for uncertainty. That excess capacity becomes survival margin when systems fail. After earthquakes in places like Japan and California, reinforced concrete hotels have repeatedly remained structurally intact, while older soft-story residential buildings collapsed. The implication is direct. In a collapse scenario involving aftershocks, severe storms, or urban fires, structural integrity becomes the first filter for survival. Escalation occurs when secondary hazards begin: gas leaks, debris fall, civil unrest, and those inside reinforced buildings are shielded by design thickness measured in inches of concrete and layers of gypsum board. Structural endurance buys time. Time is the most valuable commodity in collapse. The second factor hides in plain sight: water storage. Modern hotels are water-intensive systems. Guest rooms, laundry operations, kitchens, cooling towers, pools, and fire suppression systems demand continuous supply. To buffer municipal fluctuations, many multi-story hotels incorporate rooftop tanks, intermediate pressure tanks, or large-diameter plumbing risers that hold substantial volumes even when supply stops. Fire sprinkler systems alone contain thousands of liters pressurized within pipes. There is a common misunderstanding that once municipal water pressure drops, buildings are instantly dry. That is inaccurate. Gravity-fed rooftop tanks can continue supplying water for hours or days depending on usage rates. Even in buildings without dedicated storage tanks, the vertical columns of water trapped in risers represent stored volume. The hidden science is hydrostatic pressure and gravitational head. Water stored above provides flow below without pumps until equilibrium is lost. After hurricanes such as Katrina and Sandy, buildings with rooftop storage provided critical potable water long after city systems failed. The survival implication is profound. Water is the first limiting factor in urban survival. A single human requires a minimum of 2 to 3 liters per day for drinking alone, not including sanitation. A 200-room hotel with even a modest rooftop tank can hold tens of thousands of liters. Escalation begins when occupants panic and overuse supply, contaminating systems or draining reserves. Controlled rationing within a hotel structure could sustain dozens or hundreds far longer than a typical apartment building with no storage buffer. Water buys days. Days allow adaptation. The third feature is compartmentalization. Fire codes require hotels to isolate rooms with fire-rated walls and self-closing doors. Corridors are separated from stairwells by fire doors designed to resist flame spread for specified durations, often 1 hour or more. This is not aesthetic. It is based on fire dynamics research showing that smoke, not flame, kills most victims. The misunderstanding is that these doors are merely privacy features. They are engineered barriers. The hidden science involves fire load calculations and smoke migration modeling. By segmenting fuel and oxygen supply, compartmentalization slows flashover and buys evacuation time. In collapse conditions where power outages increase candle use or improvised heating, fire risk multiplies. Urban fires historically spread through continuous wooden construction. Hotels interrupt that continuity with gypsum, insulation, and rated assemblies. Evidence from high-rise fires demonstrates that properly functioning compartmentation can contain fire to a single unit for extended periods. The survival implication is that controlled interior zones allow staged occupancy. Sections can be sealed to conserve heat in winter or isolate contamination. Escalation occurs if ventilation systems fail and smoke spreads unchecked. But the physical barriers remain passive defenses requiring no electricity to function. Compartmentalization is silent protection. The fourth element is vertical defensibility. Hotels are built with limited access points, monitored lobbies, controlled elevators, stairwells terminating at specific floors. In normal times, this is about guest management and theft prevention. In crisis, it becomes security geometry. The misunderstanding is that multiple floors equal vulnerability. In fact, elevation is historically one of the strongest defensive advantages in urban survival. Gravity resists intrusion. Stairwells can be monitored. Elevators, once disabled, eliminate rapid vertical assault. The hidden science is crowd flow modeling and egress design. Hotels are designed to evacuate hundreds quickly, meaning stairwells are wide, enclosed, and structurally protected. Those same shafts can be controlled to restrict entry upward. Evidence from civil unrest events shows that buildings with limited entry points are easier to secure than sprawling complexes with multiple ground-level doors. The survival implication is clear. In scenarios of social breakdown, defensibility without complex fortification is rare. Hotels offer chokepoints by design. Escalation emerges when desperate populations search for resources. A structure with height, visibility, and hardened entries becomes strategically valuable. Control of access equals control of safety. The fifth overlooked capability is independent power buffering. While few hotels are fully energy independent, many maintain backup generators for emergency lighting, fire pumps, alarm systems, and sometimes limited HVAC or kitchen operations. Even when generators are not sized for full occupancy, they preserve critical circuits. The misunderstanding is that backup power is insignificant if it cannot run everything. The hidden science lies in load prioritization. Emergency panels isolate life safety loads from convenience loads. A small generator sustaining stairwell lighting, water pumps, and refrigeration dramatically alters survival calculus. Evidence from hospital and hotel operations during blackouts shows that targeted power continuity reduces mortality and chaos. The survival implication is that refrigeration can preserve food stores, sump pumps can prevent flooding, and minimal lighting reduces injury. Escalation arises when fuel for generators runs out, but hotels often store diesel on-site in quantities regulated for fire code compliance. That stored energy becomes temporary autonomy measured in hours or days. The sixth factor is sanitation infrastructure. Hotels are designed for high turnover occupancy with constant bathroom use. That means large diameter waste stacks, venting systems, and multiple restrooms distributed vertically. The misunderstanding is that once water stops, sanitation collapses instantly. The hidden science involves gravity-fed drainage and trap seals. As long as limited water is available for flushing, gravity will remove waste downward without electrical input. Even when flushing stops, multiple bathrooms allow segregation and controlled waste management strategies. After disasters, improvised sanitation becomes one of the greatest disease vectors. Cholera, dysentery, and other waterborne illnesses spread rapidly in dense populations without sewage control. Evidence from refugee camp design shows that sanitation access strongly correlates with survival rates. The implication is that intact plumbing, even partially functional, dramatically reduces epidemic risk in early collapse stages. Escalation follows if sewer mains backup or treatment plants fail, but internal vertical stacks still provide controlled containment compared to improvised outdoor latrines. The seventh and perhaps most underestimated element is logistics storage. Hotels operate on bulk supply chains. Behind decorative facades are storage rooms filled with linens, non-perishable food, cleaning chemicals, tools, batteries, maintenance equipment, and first aid supplies. Commercial kitchens are equipped with industrial refrigerators, dry storage shelving, gas ranges, and fire suppression hoods. The misunderstanding is that these are luxury conveniences. The hidden science is inventory buffering. Hospitality management relies on par levels, minimum quantities to sustain operations between deliveries. That means surplus. Evidence from disaster shelter conversions repeatedly shows that hotels can transition faster than schools or community centers because beds, blankets, and bathrooms already exist in distributed form. The survival implication is that immediate shelter capacity is built in. Escalation appears when supplies dwindle and resupply becomes impossible, forcing rationing and governance decisions within the building population. All of these factors converge on a central insight: resilience is often accidental. Buildings optimized for one purpose can outperform intentionally prepared structures when crisis conditions align with their design strengths. Hotels concentrate structural strength, water storage, compartmentalization, vertical defensibility, partial power redundancy, sanitation capacity, and logistical stockpiles in a single footprint. They were engineered to protect strangers temporarily from liability and inconvenience. Under collapse conditions, those same systems protect occupants from exposure, dehydration, fire spread, and chaos. But resilience is not permanence. Every system has failure thresholds. Water tanks empty, generator fuel depletes. Security requires coordination. Human behavior under stress can erode advantages faster than structural decay. The true survival value of a hotel depends on understanding the science embedded in its walls and using it deliberately rather than consuming it blindly. In the next phase, the analysis deepens into thermal control, airflow physics, food preservation realities, and the psychological architecture that determines whether a concentrated shelter stabilizes or implodes under pressure. Right.